this point in the study, we've reached a point, I think, where there are just a few loose ends to tie up, but otherwise I can begin to summarize the results of the study on the way in which gravity works based on the conservation of energy and momentum. I'm going to start with Newton's equation because this is so fundamental and has been in use for so long, and most of the time it's quite adequate for the purposes that we have. It works extremely well when you're dealing with the kind of observations we can make in the universe of the way in which gravity works. For example, the weight of something at the surface of the Earth, or for that matter at the surface of the Moon, and I'm sure of any other body. The equation gives you an accurate measurement of the force, which is the same thing as weight. And the equation is that the mass of the body that's providing the gravitational force plus the mass of the body that's being weighed multiplied by the universal gravity constant g and divided by the square of the distance between the centers of gravity of the two bodies gives you the force that we call the force of gravity, and which is the same thing as the weight of an object. And I'm going to analyze this equation, and particularly the unit gravity constant, because there's some very interesting conclusions you can come to. I'm going to start by applying it to a circular orbit, where in the case of, for example, the Earth and the Moon, the Earth at the center, the Moon orbiting the Earth, the mass of the Earth, the mass of the Moon, multiplied together gives you what it amounts to a multiplication factor to tell you how much the strength of gravity is. Mass does not actually cause gravity. It is a way of measuring or determining the full extent of the force of gravity, because it represents the number of lines of force, if you like, between the two bodies. And the gravity acts, one unit of mass on one body acts against the mass of another unit of mass in the other body. And so when you multiply by the product of the two masses, you get the total effect of gravity. That's really all that mass does. G is very interesting. It's called a natural constant, but I have doubts about whether it's a natural, but we'll discuss that later. Divided by the square of the distance between the two bodies, which in the case of the Moon, of course, this is very much out of scale, because the Moon and the Earth are very much smaller than this compared with the distance between them, which is about 237,000 miles, and the Earth, you remember, is about 8,000 miles diameter. The Moon is one-third of that in diameter, which represents about a 27th or 30th, if you like, of the mass of the Earth. And I'm going to now also, as I say, this for bodies such as the Earth and the Moon and the planets and the Sun, this equation works extremely well. And to study this more carefully, we're going to look at G in more detail. Now, G has the dimensions of length cubed. G represents the length cubed divided by the mass, by a mass, divided by a time that is squared. That you see when you put a cube of length in here and mass down here and time squared here, this comes to the same dimensions as force, which is mass times acceleration, or in other words, it's equal to, has the dimensions of mass times length. See if we get a better, I don't think we do have a better one. Mass divided by times the length divided by the square of time. Those are the dimensions of force, mass times acceleration. And when you substitute these dimensions in here, they come to the same dimensions. This is called dimensional analysis, and it's a very useful way of checking an equation to see whether it has the right dimensions. I'm going to now substitute these values into this equation, so we see what the equation looks like as a whole. You've got the length here, which I'm going to change to an r. It was a length, but r is a radius or length, divided by a mass and times a time squared. And this is what the same thing as a force. In fact, that's the same equation with these individual values substituting for the universal gravity constant. And the first thing that we can notice is that these are the same kind of units. I use a capital R. I'm sorry, capital R. It's easier to draw than a lowercase r, but it's the same thing really. Notice that we have here the length both in the numerator and in the denominator, and they cancel one another's out. Also, one of these masses is cancelled out. And I was interested to find out what length, what distance does that represent, what time does that represent, and what does that mass represent. And after some experimenting, I found that if you take any planet in our universe, or you can take the moon and the earth, and you substitute, say, let's take say Venus and the sun. If you take the distance between Venus and the sun and you cube it, and you take the mass of the sun and the period of the orbit, circular orbit or roughly circular orbit of Venus, square it. This is not in cycles per second. It's important to note that nature does not use cycles per second to represent a frequency, and it does not use seconds per cycle to represent period. It uses a radian, which is the length of the radius of a circle measured around the circumference. So this is in seconds per radian. If you substitute this for Venus, you find you get a value for G of 6.67 times 10 to the minus 11 cubic meters per kilogram per second, and that's exactly the same as the books will give you for the value of G. In fact, I've done this for all the planets, and it's on the Father Physics website. There is a table showing G as calculated, not from the textbooks, but calculated from the information we can get from NASA about each of the planets, and they all come to 6.67, to within 3 or 4 significant digits, which is extremely accurate for that particular measurement, which is not too well known anyway. So this then really means the distance between the two bodies, and this represents the period of the orbit of those bodies, and this represents the mass of the central body, the Earth in the case of the planets, and the the Earth in the case of the Moon, and the Sun in the case of the planets, which of course means that this cancels out one of these masses here, which leads you to the extraordinary conclusion at first sight that the mass of the Earth has nothing to do with the gravity so acting on the moon, and that the sun has nothing to do with the planets. But that's not true, because the period actually is also depends upon the mass, and that's where the mass comes in. But if you then also take this distance squared here, and here you have the distance cubed, you find that that comes down to a single distance, a single r, 3 minus 2, so that we can substitute keep the mass of the planet or the orbiting body, and put in here the period, and we can say that the force of gravity is equal to the distance divided by the period times the mass. And this is a quite different conclusion you would reach from this equation, because it suggests that the force of gravity increases with distance in proportion to the distance. And this is a very interesting, it doesn't alter the fact that this equation is correct for circular orbits, but it does tell you that the equation is true for circular orbits and not necessarily for orbits that are not circular. And in fact, one conclusion I've reached is that is the force of gravity at the moon's distance from the Earth for a body that's not orbiting, a body that might be motionless, the force of gravity, I make possibly as much as 100 times greater than this equation would suggest. That's an extraordinary conclusion, and we'll discuss that in more detail at another time. Well, now, the next thing I want to say is, and this is further confirmation that the equation is true only for circular orbits, and that is that if you now simplify this in a different way, take two of those distances and divide by two of those times, and you get the velocity squared. I must get stronger. And you are left with one of those radiuses, which cancels out one of these, and you get v squared over r for the acceleration, and mv squared over r for the force. And this, of course, is the same equation for centrifugal force. And this says to us that the moon stays where it is because it has a centrifugal force that is equal to that, and it's the force that is exactly the same as the force of gravity. And we'll be talking on a later video about alternative explanations, because nature is full of them. Alternative explanations. It's even got as far as scientists saying that there are multiple universes, or rather that the universe exists in several forms, and that different phenomena can be explained in different ways and even have different values. It's called multiple universe theory. And here we have a multiple variable, multiple function, if you like, that this equation tells you that the moon has a centrifugal force of v squared over r, and the same equation in different forms says that that's equal to the force of gravity. This is why the moon stays just where it is. So this is, I think, an interesting set of conclusions we can draw from the equation, and we'll talk about that in more detail later, but this will be enough for this video. So thank you for watching. Okay, I'll switch it off now.